All right, chemists, let's get started. So plan is for today is to finish up chapter 19, chemical thermodynamics. We'll finish our discussion of delta G, Gibbs free energy, and how it relates to our favorite rate constant, big K, or sorry, equilibrium constant, big K, that we've been talking about for the past 3 months. I told you it's coming back. It's kind of embedded itself into all of the rest of these chapters a little bit. And so we'll finish off the different ways we can ask you about delta G on exams, but I want you to recognize that all these questions that we're about to do are very, very similar. It's just the strategy to get to the answer is a little bit different because we have a lot of tools to do that. So we'll finish up chapter 19 with these last couple slides and then move on to electrochemistry. If you downloaded the slides earlier this week, I just asked that you download them again. I made some updates last night. So if you could have the latest ones, that would be great for the rest of this class. All right. So let's finish talking about these 3 different equations that I've introduced in the past couple lectures and see what's up with this question. Okay, so let's use the provided information and calculate the equilibrium pressure of CO2 that is present in this reaction at equilibrium at 298 Kelvin. So this question is asking for equilibrium pressure of CO2. I have a blank there for what Kp is for this chemical reaction. So let's remember how to write a K expression. It's products over reactants, but only things that are gases or only things that have concentrations. So simply, the K expression for this reaction is equal to the pressure of CO2 in this vessel. And that is it, because the only thing that has a concentration, the only thing that is a gas in this reaction is CO2, and it's on the product side. Everything else is a gas. That's great. So if this question is asking us to calculate the equilibrium pressure of CO2, really it's asking what is Kp? So if we look at our inventory of equations, there's only one equation that has K in it. We want to calculate equilibrium constant. So that is that first equation. It's the only one with K in it. So it seems like we need delta G. What is delta G of this reaction? I didn't give that to you, but what I did give you was thermodynamic quantities. So I gave you the delta G's of formations for the products and reactants. So in order to get delta G of this reaction, so I can get K of the reaction, I simply need to do products minus reactants because I was mean and I didn't give you delta G of the reaction directly. But products minus reactants is already a skill that we know. So we just have to be careful with our subtraction and checking what is a product, what is a reactant. So I've highlighted them here. The 2 yellow ones are our products, and then the 1 pink one is our reactant. So simply to get the Gibbs free energy change of this reaction, we are using these table values. So delta G of this reaction is simply negative 394.4. That is CO2. We're going to add negative 187.9. All of this is in kilojoules, and everything's a 1-to-1 ratio, so that's nice. Minus all of the reactants, but we only have 1, minus 625.5. Perfect. So this is our Gibbs free energy change for this entire reaction, and I have it down there. It is positive 43.2 kilojoules per mole of this reaction. So it's an endothermic reaction. So now we have the piece of information we need for that first equation to calculate K, the equilibrium constant for this reaction. Do note that R, the unit of R, is joule per mole Kelvin, so it's best if this delta G value is also in joules. So instead of kilojoules, it's best for us to convert that into joules before we plug it into our next equation. Delta G equals negative RT ln K. So we're solving for K here. So delta G, 43.2 times 10 to the 3 joules equals R, so 8.314 times the temperature, so 298 times natural log of K. So simply put everything together on one side and isolate natural log of K, and then we can take the e to both sides to get that. But I will show that work here. So 43.3 e to the 3 divided by 8.314 divided by 298. So I get that natural log of K is equal to negative 17.5-ish. And so to isolate the K, we just take e to both sides, and then we get K. So we see that K is a very small number here. It's e to a negative large number. So our equilibrium constant is equal to times 10 to the negative 8. And this is also equal to the partial pressure of CO2 at equilibrium if we have this solid sitting out there. So what we see here is that this reaction is not very spontaneous in the forward direction. We don't make a lot of product for a couple reasons. Delta G is a very positive number. Positive delta G's typically mean non-spontaneous forward reaction. We would see and predict more product being formed if delta G was a negative value. So the lesson here is we used table values to calculate delta G. Table values. These table values are only good at standard conditions and standard temperature. Standard temperature means 298 Kelvin. So notice how this question asked it in 298 Kelvin. So we were able to just use that delta G value from the table because they are measured at 298 Kelvin. So do recognize that these table values, again, only good at 298. We do make a small assumption for the next question is that yes, these table values, that delta G, those delta G's of formation, again, only good at 298. But we do make an approximation that delta H and delta S don't change considerably with temperature, but delta G does. So that allows us to calculate delta G another way. And this is especially useful if we have to calculate delta G at different temperatures. So let's approach this question. All right, using the provided information, calculate the equilibrium pressure of CO2. Oh, it's just this again. At 298 Kelvin, so still at equilibrium, or sorry, at standard conditions. So I just copied and pasted the last slide. Again, it might look like the exact same question, but the information I provide to you is different. So look at the previous slide. What thermodynamic quantities did I give you? I gave you delta G's, and that allowed us to calculate delta G of the reaction. But did I give you delta G's in this one? No, I didn't. But I did give you delta H's and delta S's. So what we're going to do is still do products minus reactants, but instead we're going to calculate delta H of our reaction. We're going to calculate delta S of our reaction. And if I know delta H and delta S of the reaction, looky here, and I know what temperature I'm running it at, I can calculate delta G of the reaction, all right? So we're just gonna jump through a couple hoops to get delta G here. So it's actually the same question, exact same question, but we're gonna arrive at the answer a little bit differently because of the information I give you. And this one is a little bit harder because we're not calculating delta G directly. And then once we have delta G, and what we'll see, it's the exact same number as the previous example, then we plug it into this first equation to calculate K, our equilibrium constant. So we just have some more hoops to jump over. So we're still gonna do products minus reactants for all these things, but we're doing it for delta H and delta S of our reaction. So I'll go ahead and highlight. Here are our products. Here are our reactants, because I don't want to mess them up. So for delta H's, watch those negative signs. We have negative 393.5 plus negative 217.3 minus our reactant lead carbonate, so negative 699.1. I'm going to point out that there is a homework question exactly like this. I just helped people with it this morning. All right, and then that equals something. So delta H of this reaction, I have it there in the corner, is 88.3 kilojoules per mole of reaction. So there's our delta H. And now delta S. Do note that the unit is a little bit different. It's joule per mole Kelvin, so it's not kilojoule, it's joule. So you got to make sure that those units match. before we move on to the next step. I like entropy because all the numbers are positive. I feel safe subtracting positive numbers. Minus 131, there we go. All right, so the entropy change for this reaction is something like, oh, it's in there in the corner, 151.3 joule Kelvin. Okay, so I have delta H and delta S, so I'm going to use the delta G equals delta H minus T delta S equation first. So I can calculate Gibbs free energy because I wasn't given it exactly. So again, you want to make sure that these energy units match. So I'm going to use 88.3 times 10 to the 3 joule for delta H. And the reason is because I'm going to move on one more step and I have to divide by R in the next step. So I want everything in joules. If delta G is in joules, it makes it easier for that next step. So plug and chug here. So 88.3 times 10 to the 3 joules minus temperature. So we are at standard temperature, so 298 again, Kelvin times the entropy, 151.3 joule Kelvin. And so you do see that the Kelvin units cancel and we're left with a delta G value that's in joules. And so we get at 25 degrees, delta G is 43.2 times 10 to the 3 joules. So scroll back to the previous slide and look at our delta G value there. What number is it? It is the same exact number. So what I'm trying to show you is that the delta H's, the delta S's that we calculate using thermodynamic quantities are related to delta G's, but only at 298 Kelvin because they are measured at standard temperature there, right? So this delta G value is the same number we got up here, 43.2 times 10 to the 3, right? They're all related via this equation, delta G equals delta H minus T delta S. Again, at 298 Kelvin, all these values will be related to one another when you look at different reactions. If you calculate the delta H's, delta G's of reactions for those things. Okay, so this actually isn't even our answer. It's only part of the answer. I just got delta G using this, the thermodynamic quantities, delta H and delta S. So the actual answer to this question utilizes this first equation. Now that we have delta G, we just got it in a much more annoying way, a longer way. To get to the same point, we're going to set this delta G value we just got equal to negative RT natural log of K. We're going to solve for K and recognize that that temperature is equal to 298 Kelvin because this is at standard temperature, standard conditions, right? And we'll get the same answer, okay? So we just got delta G in a different way here. We did products minus reactants of delta H and delta S before using this equation, delta G equals delta H minus T delta S, to predict what is delta G at different temperatures. In this case, it's 298, and it matches the textbook, those thermodynamic quantities exactly. Okay, so let's do it a little bit differently now. But this time, it's the same exact question, but I've changed it a little bit. All right, so this time, using the provided information, calculate equilibrium pressure of CO2, so same exact thing, but this time, are we at standard temperature? We are not. We are not at 298. We are actually at what, 400 degrees Celsius. So I cannot use this delta G value. When is this delta G value true? At what temperature? 298, and that's it. So we cannot use this value. We can't use it because, again, that is only good at 298 Kelvin. But what we can do is make the approximation that delta H and delta S are constant with temperature, all right? They're constant with temperature, and so we're going to use this third equation first. We're going to calculate, well, what's the new delta G value at this new elevated temperature based upon delta H and delta S of this reaction. Then we can plug that delta G number into our K expression, just like we did before. So really, this question just is exactly like slide 35. It's just instead of at 298 Kelvin, we're operating at 673 Kelvin. So we need to get the correct delta G first at this elevated temperature, then plug it into that K equation. So we don't have to do products minus reactants here. I already gave you the deltas of this reaction. So simply, I'm calculating what is my Gibbs free energy change at 673 Kelvin. Given this new temperature and assuming delta H and delta S do not change with temperature. So essentially what I'm doing is using these thermodynamic knowns. Our temperature here is 673 Kelvin times delta S of our reaction. We know these values, and so we can calculate delta G. So simply, I'm going to convert delta H to joules again, because it needs to be in joules for the next step anyway. So there's delta H minus this new elevated temperature, so 673 Kelvin. And times delta S, so 151.3 joule Kelvin. Oh, there should be a Kelvin down there, whoops. And so we get that the new delta G at this elevated temperature is equal to some number, negative 13.5 times 10 to the 3 joules. All right, so this reaction's a little bit more spontaneous at higher temperatures, it seems. So not our answer, okay? All we did was plug in the values and temperature given to get this new delta G value at elevated temperatures, because delta G does change considerably with temperature, but not delta H and delta S. And now we simply stick this delta G into the negative RT ln K expression, where T is now 673 Kelvin, and then solve for K. So K, in this case, if you move everything around and take e to the both sides to get rid of that natural log, you get that K, which is also equal to the partial pressure of CO2 at equilibrium, is 11.2 atmospheres, right? So this slide is no different from the previous slide, okay? But the only difference is recognizing we're at an elevated temperature. You have to use other thermodynamic quantities, delta H and delta S of the reaction, to calculate Gibbs free energy at this elevated temperature. Then we can go ahead and calculate equilibrium constant. Oh, I just thought of this. Let's use Le Chatelier's principle real quick, okay? Real quick. Okay, so let's go back to a simpler time when we were in chapter 15. So in this question, I tell you delta H it's endothermic, okay? So let's think about this. If this was chapter 15 and we were doing Le Chatelier's principle, and I told you this reaction was endothermic, where does triangle go? You remember triangle? Sweet, sweet triangle. Where does he go? On the products or the reactant side? The reactant side, perfect. All right, so if you heat this reaction up, which way does the reaction go? Forward. So what should you observe? The pressure of CO2 increase when you heat it up. Is that what we just got? What is the partial pressure of CO2 at this elevated temperature? It's 11 atm. What was it at room temperature? Tiny. So what we just proved via chemical equilibrium and free energy is that the equilibrium constant increases when we heat up this reaction, and that's exactly consistent with Le Chatelier's principle when we put triangle on different places and predicted which way a reaction shifts. But here we're actually numerically calculating it, right? So I don't know what you like more, the concept or the numbers. I imagine you all like the concept more. You all are really good at Le Chatelier, but with the numbers, it's a little tougher. But that's basically, consistent with all of the observations we've made previously. All right, so that's it. Okay, so let me just finish off this chapter, sorry. And I was supposed to get to this point last class, but I didn't, where I showed the demo where I did a combustion reaction, the hydrogen balloon reaction up here. showing you, hey, that's a really fast reaction. It's between gases. Versus the thermite reaction, where that reaction is between two solids. It's still spontaneous, but it was a lot slower. We were able to kind of watch it progress while the hydrogen balloon experiment, you blink and it's done, all right? So what I'm trying to get at is that thermodynamics that we are talking about right now, delta G, negative delta G's mean spontaneous, does not necessarily mean that a reaction is fast. That's chemical kinetics. That's completely separate from what we're talking about now. Let me just go to this slide real quick. What we talked about in chapter 19 is the relative energy of products and reactants. That's what we're talking about. Oh, this is a decrease. This is a negative free energy change. So this is a spontaneous reaction. But spontaneous does not necessarily mean fast. Fast means activation energy. They are mutually exclusive from one another. All right? So let me show you this example. Okay, here's two reactions. So diamond is made of carbon. So if I add and react carbon and oxygen together, I get CO2. That's a combustion reaction. So tell me, based upon the information I've given you here for this reaction, is this reaction, this combustion reaction, spontaneous? Can you burn diamond? Will diamond catch on fire and burn by itself once it's on fire? It will. Because why? Delta G is negative, yes. I mean, what I'm saying is that, yes, or if you are wearing a, diamond jewelry, it's not going to, combust on itself spontaneously. But if you did catch it on fire, once it started burning, it will burn to completion by itself. Okay, so this reaction is spontaneous because delta G is negative. Is this reaction fast? Do combustion reactions happen fast? Just think, will a combustion reaction finish in your lifetime? Yes, so it is rather fast. Yes, it is. In the grand scheme of things, like it'll finish before our lifetime's over, or even before like the day is over. Okay, now let's look at this other reaction. Here's diamond, also carbon, it's a solid. And then here's graphite, also carbon, a solid. So it's they're allotropes of one another. So I went ahead and went into the textbook and got the thermodynamic quantities of diamond and graphite. And I got this. The conversion between diamond to graphite has this delta G value. So tell me, is the conversion of of diamond to graphite, note the direction here, is this spontaneous? It is. Why? Delta G is negative. Yeah, that diamond has more energy than graphite. Graphite's more stable. But is this reaction fast? No. If you just use your intuition, if you're wearing diamond jewelry, will that diamond convert to graphite in your lifetime? It will not. That's not something we hear about. If diamond did convert spontaneous to graphite, there would be a lot of uproar in this world, but it's not like that. So obviously we're seeing the consequences of the difference of kinetics here. This reaction, even though it's spontaneous, this reaction is not fast. Converting diamond into graphite is not fast because kinetics and thermodynamics are separate from one another. Again, diamond to graphite, the energy difference here, that is thermodynamics. Kinetics is everything that's in between, the mechanism in between. So clearly for this diamond to graphite conversion, yes, going from diamond to graphite's downhill, it's spontaneous, but there's just this huge activation barrier to preventing diamond from converting to graphite, so it just doesn't happen in our lifetime. If you Google it, it's something like 1 billion years it takes for, diamond to convert to graphite. But what I find funny, and if you followed me into the darkness over the past year from 1210, you know that I'm a millennial. I eat avocado toast. I don't buy diamonds for ethical reasons, but here's another reason, okay? So let's go back here. What's the saying about diamonds? Diamonds are a girl's best friend, whatever, but the other one, diamonds are forever. So based upon the numbers we just got, is diamond forever? It is not. No, that would violate the second law of thermodynamics. No, we just learned here that no, diamonds actually are not forever due to the second law of thermodynamics. So that's like completely wrong, that whole saying. They're not forever, because spontaneously, based upon the value of delta G, they will spontaneously convert to graphite given enough time. Yes, so there's another reason to hate on diamonds. Okay, all right, so that's it. That's chapter 19. We did the 2 demos, also showing, hey, yeah, we have 2 delta G's negatives. These are 2 spontaneous reactions. It may look like the second reaction is more spontaneous because there's a, it's more negative, it's more spontaneous. But what we saw is that the reaction, the thermite reaction, was a lot slower, not because of the value of delta G, but because of the states of the molecules actually colliding with one another. That there was a large activation energy between solids, but very small one within gases there. Okay, so, and then I would have done the demo here, but I did it, on Tuesday, so sorry about that. Okay, so that is chapter 19. So we will move on to chapter 20. And again, if you got the slides earlier in the week, just re-download them. Okay, so I like chapter 20, electrochem. It's very different from what we've talked about in previous chapters, and I think it's very applicable. And it's another instance where, you know how sometimes we teach you the concept first and then the math? Or sometimes we teach you the math and then you apply the concept, Like we've done that with weak acids and weak bases. When Ka is big, that's a strong weak acid, but then its conjugate is very weak. So that whole idea, we showed you the concept, but then we showed you the numbers, I think later, or maybe first, I forget. But the concepts are related, that we said, oh, stronger the weak acid, weaker the conjugate base, and it has to do with the magnitudes of Ka and Kb. Okay, so the numbers, that's an example of the numbers matching the concept. So here it's the same thing, except you guys already know the concept. You know the concept of electrochemistry and spontaneous reactions from Chem 1210. When we talked about the activity series. Remember the copper cycle in the activity series? Well, we're now going to show the numbers that go along with it. So hopefully all of it comes together of like why the activity series works. So a lot of these concepts are going to come back, so I'm going to do a little bit of review. Do memorize N-ox, red cat, and I think the other one is Leo goes grr. Yeah, to help you with half reactions. N-ox means anode oxidation. Red cat means reduction cathode. Leo goes grr, what does that mean? Loss of electrons is oxidation. Gain of electrons is reduction. I don't memorize those. I just look at numbers and I see, oh, do they go up or down? And that's how I know it. Anyway, so we're going to do a little bit of review. A lot of this builds on chapter 4 from Chem 1210. Oh, I'll point out that this is the second to last chapter we cover in 1210, or sorry, 1220, and then you're done. You're done and we're at the end of the tunnel, and this is the last long chapter. Chapter 21 is really short. Okay, but this one's the last really long chapter. It's so long that only part of it is on midterm 4. So here I have that up here, where here in the first part of the chapter, here are all like the numbers, all the numbers and the concepts. The last chapters are more application of these concepts. I like the end of this chapter. We'll talk about batteries and how cool batteries are. We'll talk about potato power, why this picture is a little misleading, and talk about voltaic cells, and again, why certain types of redox reactions are spontaneous and others aren't. Because this chapter is split up into 2 chapters, I split up the homework set. It's still the same number of questions I give every year, it's just I split it up into 2 different sets. One is that covers midterm 4 material, and the other one that's going to be assessed on the final. So you'll see 2 sets there. One's a longer set and one's fairly short. Okay, so that's the outlook there. Okay, so I told you this is the review stuff. So this is a single displacement. Sorry, this is a mistake in my slides. That's a mistake. Okay, That's a single displacement reaction. In Chem 1210, we asked you a lot of different questions about this single displacement reaction. You technically should already know the answers to all these, right? Could be, 1, is this reaction spontaneous? We asked that to you in 1210, but really, now that we just finished chapter 19, if we asked you, is this reaction spontaneous, what were we actually asking you? Is delta G negative for this reaction? But obviously you didn't know what delta G was then, okay? You didn't know what it was, but that's what you were doing behind the scenes, predicting, okay, when is delta G negative for this reaction? Is it spontaneous? Other questions, we asked you, what is the net ionic equation? What are the strong electrolytes? We also asked you, which element is oxidized, which one's reduced, what's the oxidizing agent, what's the reducing agent? All these things are still important, and we're gonna review them. So, this first one is this reaction spontaneous? That's when we use the activity series, right? We looked at, oh, the metal is here on the activity series, there's copper, and we are reacting it with silver plus. So the metal solid, the solid metal's higher on this activity series than the ion, so this was a spontaneous reaction. You put copper solid into a silver plus solution, and you will see silver solid plate out over time. So we'll talk about that in a second. So let's review. The first one is oxidation numbers. In order for us to determine what is oxidized and what is reduced, instead of thinking, oh, what's losing electrons and what's gaining electrons, because sometimes it's hard to imagine that, is if you just get the oxidation numbers of all the atoms and track them. Does this element increase its oxidation number or decrease? That's how you figure out whether it's being oxidized or reduced. So simply, oxidation number is charge. If an atom had a charge, that is its oxidation number. So here's some rules. The first one is any element already in its like neutral state, any element, atom, that is already charged neutral has an oxidation number of 0. So oxygen gas, hydrogen gas, all of these solids, they're charge neutral. There's only one element there. They all have a 0 oxidation number. If things are charged, so if things are part of an ionic substance, its charge is its oxidation number. So silver plus has an oxidation number of what? +1. Zinc, +2. Iron 3 plus, +3. Chloride -1. Perfect. If you think charge for oxidation number, you'll be right 99% of the time. Let me skip number 3. Let's do 4 and 5, because these ones are helpful for us to apply rule number 3. Okay, so if oxygen is in a compound, if it's in a compound, like CO2, oxygen will almost always be a -2 oxidation number. And that helps us, right? If you know that oxygen is -2 in CO2, then what does carbon have to be? +4, has to be +4, okay? Except in O2, all right? Don't say that in O2 oxygen is -2 here. This is not a compound. This is an element, so this one, O2 is 0. So don't forget that one. Also, hydrogen, when it's present, it helps us figure out the oxidation number of everything else. So oxygen is almost always +1. That's the most common. Sometimes you'll see -1, but that's less common. Hydrogen is +1 when it's attached to a non-metal, something like HCl, NH3. All of those things, hydrogen has a +1. Hydrogen will sometimes have a -1 when it's basically acting as the anion, which is very unlikely, but something like lithium hydride or calcium hydride. Those are examples of hydrogen with a -1 oxidation number, because it's basically acting like an anion because it's attached to a very positive cation. But that's uncommon. We never work with lithium hydride or calcium hydride. We don't work with those. We usually see hydrogen with nonmetals. All right, so those rules help us with rule number 3, recognizing, okay, all oxidation numbers have to add up to the total charge of your substance. Really nice if it's charge neutral, but you can also do it for an ion as well. And so here, again, if you think charge and kind of the special rules with oxygen and hydrogen, you'll be fine. So iron chloride. Chloride has a -1 oxidation number. But there are 3 of them. So what does that make iron? Plus 3. That's it. See how the oxidation numbers add up to the charge. Cool. Now let's do nitrate. I don't know nitrate, or sorry, I don't know N, the N in nitrate. That's not quite clear. So I can use the trick, oh, oxygen is almost always -2. So if oxygen is -2 and there's 3 of them, what does nitrogen have to be? +5, because it has to add up to -1 because that's the charge of nitrate. All right, if you think charge, you'll be fine. So let's keep going. Let's review a little bit more. Let's assign the oxidation numbers to all these things. Hydrogen and hydrogen, what is it? Just yell it out. 0, perfect. Bromine and bromine, 0, okay. Hydrogen and bromine in HBr. In hydrogen, it's what? +1, bromine, it's -1. Yes, if you just think charge, you think, oh, you put HBr, the strong acid in water, you get H+ and Br-. The charges are its oxidation numbers. Okay, calcium chloride. This is ionic. So simply its charge. Calcium's going to be +2. Each of those chlorides are going to be -1. Each of them, because there's 2 of them. All right, chromium and oxygen in this chromium compound. So we're going to use the trick. Which one do you know already? Oxygen's -2. All right, and so if we look at the compound, there are there's 3 oxygens. So that gives a total -6. So in order to make this whole compound charge neutral, all those chromiums have to contribute a +6. So that makes chromium +3. It's basically charge. Right, keep going. Manganese in permanganate. Again, oxygen's the one we know, -2, but there's 4 of them. So there's -8 coming from oxygen. What is manganese? What does manganese have to be? So the overall charge of the molecule is -1. Manganese has to be +7. Yes. All right, all of the atoms in that is calcium oxalate. But we'll go through it anyway. Calcium in an ionic compound is going to be +2. It's a metal cation. Oxygen, -2, but there's 4 of them. And this whole thing has to add up to 0 because the compound's charge neutral. So you just kind of look at all of the charges and think to yourself, what does each of those carbons have to be in order to make it charge neutral? Note that there's 2 carbons. So I think, okay, calcium is a 2. There's -8 coming from oxygens. So if this is +6, then that's charge neutral. But that +6 is coming from 2 carbon atoms. So that means 1 carbon atom is equal to a +3. And then you could add it all up yourself to check your work. +2 plus 3 times 2 minus 4 times 2 gives you 0. Right? So if you just think charge, you'll be good there. And this will be useful for us to identify what is being oxidized and what's being reduced in a reaction. Okay, so now that you know oxidation numbers, you can track an element and determine is it being oxidized or reduced in the course of a reaction. So yes, you can memorize Leo goes Gur, that loss of electrons is oxidation and gaining of electrons is reduction. See, I don't even like to memorize it. I just look at oxidation numbers. If an oxidation number for an element goes down, its oxidation number goes down, it's being reduced, then that substance being reduced if its number goes down. If the oxidation number for that element or atom goes up, the oxidation number goes up, so it's being oxidized. So I just look at the numbers and look at how they change, all right? So what we see here in this example, you've done this in lab. You took a magnesium strip, you put it in acid, you saw it disappear, and you saw bubbles being formed. So what we see here, magnesium, is going from a 0 oxidation number to a +2. So its oxidation number is going up, so magnesium solid is being oxidized. I don't like to think, oh, magnesium is losing negative electrons. I don't like to think that. I just think, oh, it's being oxidized, its oxidation number goes up. Versus hydrogen is going from plus 1 to 0. Its oxidation number is going down. It's being reduced. H plus is being reduced to hydrogen gas. Right? Or yeah, you can think it's gaining electrons too. It's all consistent there. Right? So, and now that we know oxidation numbers, we can do that. So now to actually predict whether this reaction happens or not. Meaning, we know, so like you know, you've done this in lab, right? You've done it. Is this reaction spontaneous? It is. And so the reason it's spontaneous is because you were able to look at the two reactants in this reaction, locate them on the table. Here's magnesium. Where are you? Magnesium solid. So I'm getting magnesium solid, and I need to locate where H plus is. So there's magnesium solid, the reactant, and there is H plus, the cation. So the rule is a redox reaction will happen, or you can think the reaction is spontaneous as written in the forward direction when the metal is higher. The solid metal is higher on the activity series than the cation. So what we see here is magnesium solid is in fact higher on the activity series than H plus. So this reaction does happen. Right? If we did a combination a different way, all right, what if we mixed H plus and iron solid? Will a redox reaction happen? Yes, because the metal solid is higher on the activity series than the acid. So that means iron will dissolve in acid eventually. Or lead. Lead solid. Yep, that's spontaneous too. Yep, lead pipes will slowly rot away over time when exposed to acid. But what about acid and silver? No, because now the metal is lower on the activity series. This is not a spontaneous reaction. So what's the sign of delta G? Positive, yes, in this combination, because, yeah, silver's lower on the activity series. Do you want your silver jewelry to dissolve away when you accidentally spill some soda on it? No, you don't. And it doesn't, because we call these metals precious metals because they are resistant to things like acid. Silver, gold, platinum, all those things resist, dissolving away in acid, or they wouldn't be precious metals. All right, so that's review. You know how to use the activity series. But what was happening behind the scenes is, again, you were actually calculating delta G all this time. And really, it's related to the cell voltage, the cell potentials of these half reactions when you combine them in a certain way. So what's coming up in this chapter is now we're going to put in numbers here. And hopefully it'll all come together. Why does the metal have to be higher on the activity series for the reaction to proceed? So yeah, why are the metals on the top easily oxidized? And why are redox reactions only spontaneous in one direction? It's because delta G is negative only in one direction. It's positive when it's the other way. Okay, so let's answer these questions now. Okay, review chapter 4. Let's get the net ionic equation. So remember, the net ionic equation, you remove spectator ions. So I hope you can see what is the spectator ion in this full reaction. It's the nitrate. So the nitrate is the thing that's going to drop out of this equation in the net ionic equation. But let's just go through the whole thing. We need to locate what are the strong electrolytes. So you have to decide what do you split and what do you keep together. So copper, that's a non-electrolyte. So you keep all of those ions and those atoms together. But silver nitrate is a strong electrolyte, so you split that up. Silver solid, no ion, so don't split that one up. But you do split up copper nitrate, so split that one up. And so splitting everything that's a strong electrolyte gives you the full ionic equation. So let's write that out. So copper solid plus 2 silver pluses, that's aqueous, I just don't feel like writing it. NO3 minus, oh, so you mean 2 of them, sorry, 2 of them. All right, so I split up the strong electrolyte silver nitrate. And then we make 2 silvers, solids, and then we split up that copper nitrate, copper 2 plus and 2 nitrates. So how we approach full ionic equations is we cancel out whatever does not change at all on the reactants and product side. I see, oh no, copper's changing, it's going from a solid to aqueous. Silver's changing, it's going from aqueous to solid, but does nitrate change? does not. It's the exact same on both sides, so that's why nitrate is my spectator. So we don't need to include it in the net ionic equation. So let's write that. The net ionic equation is just simply copper solid plus 2 silvers, I'll bring the aqueous back, gives us 2 silver solids and a copper, 2 plus aqueous. And so, again, the point of the net ionic equation is this specifically describes what's happening in the reaction. It's focusing on the redox reaction, on the thing that's being oxidized and reduced. We got rid of the nitrate because we don't need to include it. Yes, it's there as the salt, the counterbalance the charge, but it's not participating in the reaction at all, so we can leave it out. This, the net ionic equation, is much cleaner. It's a lot nicer to look at because now you can clearly see what is being oxidized and what's being reduced. What do we think copper is doing? Is it being oxidized or reduced? Oxidized, yeah, because now the charges are really easy to see. Copper to copper 2 plus, it is being oxidized. But silver to silver solid, it's being reduced, yeah, so silver plus, because it's going from +1 to 0. So we see silver plus is being reduced, copper solid is being oxidized. Notice that I'm just pointing to the reactants. And then to get the oxidizing and reducing agent, we just swap places. So the oxidizing agent is the thing that is reduced. All right, the thing that is reduced is the thing that's taking electrons to oxidize something. The reducing agent is the thing that gives up electrons to reduce something. So it's the thing that is oxidized. So basically our answers changed. So the thing that is reduced is the oxidizing agent, so that is silver plus is the oxidizing agent, and then the reducing agent is copper solid. Notice again, I'm just pointing at the reactants. You don't point to the products. Okay, so let's answer now this question using the activity series. We are mixing copper and silver plus. Locate those on this table. Copper solid, silver plus are my reactants. So yes, the metal is higher on the activity series than the cation. So as written, this equation is spontaneous. This does happen. If I put a strip of copper into silver plus solution, we'll see silver plus slowly played out. But now let's look at and see, are these combinations spontaneous? What if we mixed silver and copper 2 plus? So locate those on our table. We got silver solid, so right there, but now copper 2 plus. Is that spontaneous? It is not, because now the cation is higher on the activity series. That does not match our thing. All right, and then the last one here, silver plus and copper 2 plus. So highlight those 2 reactants. Is that spontaneous? No, because there's no metal. Both of these things would have to be reduced. In order for a redox reaction to happen, something needs to be oxidized, something needs to be reduced. Here, we have 2 cations. We have no neutral metal for redox to occur. So this would not happen either. But why? Why don't these things happen? It's not just because of the table and the metal's higher. Again, in the background, what you were doing was actually calculating Gibbs free energy and cell potential of the 2 half reactions involved. Okay, so now this is the new stuff in the chapter. Now that I've primed you, okay, now we can get some learning done. This chapter, we're going to present to you reduction values, okay, standard reduction potentials. So in your textbook, you have lots of tables with half reactions written on them that describe the reduction half reactions potential. So what that means is that these half reactions are written in the reduction form, meaning that the substance is gaining an electron, and it's showing you what is the potential, the electrical potential created for this process to occur. So we see that some substances have very positive reduction potentials and some things have very negative reduction potentials. In general, when a reduction potential is very positive, that's a very spontaneous or favorable reaction that happens. So, like in the previous chapter, we were always looking for negative delta G values. In this chapter, we are looking for positive E values. Positive cell values, E cell values, typically mean spontaneous reactions. In turn, which means a negative delta G, which we'll talk about later. So, when your cell potential is positive, your reaction is spontaneous. This is what you did in 1210 without even knowing it, all right? But the thing is that a cell, an electrical cell, always has two components. All of these are written in the reduction form. But in a redox reaction, you need something that's reduced and something that's oxidized. So now it's even more important that you can locate what is being oxidized and what's reduced in your reaction so you can calculate the cell potential correctly. Something is going to be reduced at your cathode and something else is going to be oxidized at your anode. So you need to identify them and use the correct numbers to calculate the cell potential for your system. So what I'm trying to get at is every time you use this table and got a, yes, the reaction is spontaneous, what you actually did was calculate the cell potential, and if the reaction is spontaneous, the cell potential was positive. That is what you did. So let's do that here. These two tables communicate the similar things. Here we're talking about in oxidation. We say, oh, lithium is very highly oxidized. But on this table, it's very similar, but we're just talking about it in the reduced form, where we say, oh, silver plus is very easily reduced. So very, very similar, but just kind of opposite thinking. It's still conveying the exact same concept. So let's do these questions, but now numerically prove that, yes, copper solid plus silver plus is a spontaneous reaction. We did that already. We already said, oh yes, copper plus, copper solid is above silver plus. This is spontaneous, but why? We have to choose why. And so let's calculate the cell potential of this. So what is required is we need to decide what is the anode and what is the cathode. But simply, you already know how to do this. You need to just say, okay, what is reduced and what is oxidized? N-ox, red cat. So let's just go through it. Copper is being what? Oxidized. Silver is being reduced. So copper is our ox. N-ox, so copper is our anode. Red cat, so silver is our cathode. That's all we need. Because now that we know the cathode and the anode, we have the reduction potentials, the numbers. We just need to subtract them in the right order. Okay, cell potential is always the reduction value from the table of the cathode minus the reduction potential of your anode from this table. So we're going to take the value of our cathode, which is silver. So we're going to take the silver number. So what is that? 0.8 volts minus our anode. So the anode is copper. This is silver. And so the copper value is 0.34 volts. And so we get, yes, a positive voltage. So when you mix copper solid and silver plus, you get a positive voltage come out. That's why this reaction is spontaneous. So I flipped, see the next one, I flipped the reaction. Silver solid plus copper 2 plus is not spontaneous. When we use the activity series, we saw, oh, a reaction doesn't happen. So what do you think the sign of E cell is here? It's negative. So let's prove it, okay? We prove it by doing the same concept. Silver is being, what is it? Oxidized. So it is the anode. But this time copper is being reduced. So it is the cathode. So we need to make sure that we do the subtraction in the right order as written in this reaction in the forward direction. So we're going to take the reduction potential of the cathode. So copper, what number is that? 0.34 minus the reduction potential of the anode, which we identified as silver, so minus 0.80. So yes, we in fact get a negative voltage. So will this reaction happen spontaneously? It will not, okay? So what I'm showing you are the numbers now that predicted the same things we did in 1210, right? That these redox reactions are only spontaneous in one direction due to the cell voltage only being positive in one direction. Okay, so that's how we use the reduction table. We'll explore the reduction table a lot more in a little bit. I just wanted to share with you that you actually already know a lot of these concepts, and we're just building on it. Okay, so let's look more into redox reactions and balancing them. So here's a pretty straightforward redox reaction. You know, we can look at the table and determine, does this redox reaction happen? We're mixing H plus and zinc. It's up here. So yes, this redox reaction does happen, okay, because the metal is higher on the activity series than the cation. We can ask you what is being oxidized and reduced, so we can go ahead and get oxidation numbers of everything. And we see that zinc is being oxidized, H plus is being reduced. So that means the oxidizing agent is H plus, but the reducing agent is zinc solid, right? That's review. We did that a bunch already. Okay, but now in this chapter, what's really important is something that we've kind of ignored in 1210, is recognizing, okay, yes, oxidation is loss of electrons and reduction is gain of electrons. Notice how the electrons are funneling into one another. In an oxidation reaction, electrons, they're given up, they're products. And those products funnel into the reactant side of your reduction reaction. It's kind of like an intermediate, right? Electrons are produced and then consumed in the next step in the reduction reaction. So what isn't shown in this balanced equation is how many electrons are actually being transferred in this redox reaction. Notice how you don't see any electrons, but they're there. They're moving in the background. They actually get canceled out. Can you tell me how many electrons are involved in this process? 2. There are 2 electrons in this process. I like to think, look at the oxidation numbers. That'll help you. Zinc is going from 0 to +2. So it's losing 2 electrons. Where are those electrons going? To the 2 H pluses to make it fully charge neutral. So there's 2 electrons going there. So that's the big idea with balancing redox reactions. Not only do we have to actually balance the atoms, we actually also have to balance the electrons that are being transferred in the background. And so we have a new way to do that. Okay, so in redox reactions, electrons are being transferred, and the atoms also have to be balanced. So this one, that first one's rather easy to balance. You might just see, oh, you just need 2 H pluses and it's balanced. It's balanced with charge, it's balanced with atoms. But where it gets trickier is something like this one. This one's a lot harder to balance. So there's a certain strategy we use to balance redox reactions. It's a lot more in-depth than other kind of guessing and checking reaction balancing. So there's a certain strategy we use to balance redox reactions that I show in this slide. So we'll revisit this one. I promise you, you can't just look at this and balance it. It's a lot more involved. So here are the steps. There are 7 steps to balancing a redox reaction in acidic conditions. If you memorize these 7 steps, you'll always be right. So just learn them. Okay, so here they are. This is called the method of half reactions, where in order to balance a redox, we have to split up the half reactions, balance those separately, and then combine them back in the end. And so here's the strategy. Separate your half reactions. Figure out what is oxidized, what's being reduced, and split them up. And then we're going to balance them separately. First, you balance the elements other than oxygen and hydrogen. Then you balance oxygen atoms by adding water. And then last, you balance hydrogen atoms by adding H+. You're adding H+. That's very important here. Okay, so not only are you fixing the hydrogens, like balancing the atoms, but you're also kind of screwing up the charge, which you'll make up for in the next step. Because once now you've balanced your atoms, now you need to make sure that the charges are balanced on each of your half reactions. So balance charges by adding the appropriate number of electrons. Remember, these are half reactions. So something is either giving up electrons or accepting electrons in a redox reaction. But what can help you catch some of your mistakes is that in an oxidation reaction, electrons are always going to be your reactant. In a reduction reaction, electrons are always a reactant, versus in an oxidation reaction, your electrons are always on the product side. So if you balance your half reactions and you get electrons on the same side for both of your reactions, you did something wrong. Electrons always funnel into one another. So there's a lot of places you can check yourself. And then finally, you add up your reactions, ensuring that the number of electrons cancel one another, that electrons funnel into the next one. I think it's better if we just do examples. And then I'll do a demo. Okay, so let's balance this under acidic conditions. The reason we call it acidic conditions is because when we balance hydrogens, we add H+. All right? Hold on, balance, I don't like this. Split half reactions, balance all atoms, balance O by adding water, balance hydrogen by adding H+, and then balance electrons. Do remember those electrons are negatively charged. So let's balance this under acidic conditions. So first step, splitting into half reactions. Getting the oxidation numbers are going to help you here, because you can see cadmium is absolutely changing. It's being oxidized. Its oxidation number is going up. Nickel, on the other hand, it's going down. It's being reduced. You might be asking yourself, well, what about oxygen and hydrogen? How are those oxidation numbers changing? They're not. So we don't have to worry about them. What we care about is cadmium and nickel. So I like to write the oxidation reaction first and then the reduction reaction. So always give yourself enough space because you're going to add a lot of stuff. So in the oxidation reaction, you're making cadmium, taking cadmium and making cadmium hydroxide. So notice how I'm just taking the reactant and the product from the half reaction from the full reaction. Then for the reduction reaction, you're taking nickel oxide and then you're making nickel hydroxide. Nickel hydroxide. All right, and so what we're going to do is balance both of these separately and then bring them together at the end. Okay, so we have the half reactions. Now we balance all the elements other than oxygen and hydrogen. So cadmiums, they're balanced. Next, oxygen. Are our oxygens balanced? No. So we're going to add water, 2 of them, on the reactant side. So now there are 2 oxygens on each side. All right? Then you balance hydrogens by adding H+. Notice how hydrogens show up on both sides. So just make sure that both of them match. So I see, there's 4 hydrogens on my product side, on my reactant side, and there's 2 hydrogens on my product side. So I'm going to add 2 hydrogens, so there are 4 on both sides. Notice again, I'm adding H+. It's not just hydrogen, we're adding H+ because this is acidic conditions. All right. So once you have the hydrogens, now you balance charge. And so again, I like to take inventory. My reactant side is an overall 0 charge, but my product side is an overall what charge? +2. How can I make them match? By adding electrons. I add 2 electrons, but on what side? The product side. So +2 electrons, this is now balanced. Perfect. Right? Same strategy for the next one. We have the reduction half reaction, so we got nickel on both sides. Are oxygens balanced? Yeah, cool. Are the hydrogens balanced? No, so we don't need to add water, but we do need to add H+. So we're adding H+ to the reactant side, we're adding 2 of them. Okay, so there are my H+. So now I just need a balanced charge, and so I see there is a +2 coming from the acid, the H+. So simply I'm going to add 2 electrons to the reactant side for my reduction reaction. And so now we can simply add up these reactions and cancel anything that we can. The electrons cancel out perfectly here. So electrons funnel from one to the other, and actually the hydrogens cancel too. So we see that this reaction overall is 2 waters plus a cadmium plus nickel oxide gives you cadmium hydroxide and nickel hydroxide. Right? Those are the 7 steps. You do that every single time, you'll be right. Right? Notice here that the number of electrons in both half reactions match, but if they don't match, you need to make them match by multiplying by some type of coefficient or something. So pretend that, let's pretend the first reaction had 4 electrons. How should I add up these 2 reactions? I should add the second one, but I need to double that reaction. So if I double this reaction, then that's how I force the electrons to match, all right? So note that we got to make them match. Okay, this should be a 2. All right, and so the number of electrons that we canceled in the background is the number of electrons in this process. Okay, let's do another one. Oh yeah, we have enough time. Okay, another one. Let's balance under acidic conditions. So same strategy. Let's get those oxidation numbers. So +1, -2. Oxygen and nitrate is -2. Nitrogen is +5. Sulfur solid, 0. NO, O is almost always -2, so nitrogen is +2. So track only the things that are changing. Sulfur is changing. Sulfur is being oxidized. And then nitrogen is being reduced, yes. If you do this and you get both things are being reduced, is that possible? No, you did something wrong, and you should try your oxidation numbers again, all right? So there's our 2 half reactions. You know, we can answer these questions, whatever. What matters here are the 2 half reactions. So my oxidation reaction, again, give yourself a lot of room, is H2S goes to S. The reduction reaction is NO3 minus goes to NO. All right, let's do the oxidation first. Sulfurs, good. Oxygens, there are none, so that means they're good. 0 balances with 0 as well. Hydrogens, not good. We have to add H+. So you're going to add H+ to the product side. So there's H+, 2 of them. All right. And then last, we balance charge. What is the total charge right now on the reactant side? 0, but on the product side, it's +2. So I need to add 2 electrons to which side? Product side. So +2 electrons. Common mistakes I see is that students, they know they have to add hydrogens, but they just add H, not H+, and then your charges get screwed up, right? So 2 electrons. So now let's do NO3. So there's 3 oxygens on one side, but only 1 on the other side, so I need 2 waters. But now I have 4 hydrogens on my product side, so I have to put 4 H+ on my reactant side. Now this is the hard part. Make sure, you know, the charge is balanced. I try not to be lazy, and I just will take inventory of everything, and I'll be like, okay, right now as is, my reactant side has +3, my product side has 0. So to make them match, to force them to match, I need 3 electrons on my reactant side. And that's the strategy. Okay? Don't forget that nitrate also is charged. So it's not just, oh, I have to neutralize the H+, but you are also looking at that nitrate as well. Whoops, sorry. That nitrate has a charge as well. Okay, so now we have 2 balanced half reactions. If we just add them up as is, will all those electrons cancel? They will not. So how do I force them to cancel? You gotta multiply by, I think the word is least common multiple? Is that the right word? You know you have to multiply by a 2 and a 3, right? Yes, okay. I just don't know the math word for it. So if I multiply the oxidation reaction by 3 and then the reduction by 2, I force 6 electrons on each side and add them up. This can be tricky, okay? Because if I multiply that first reaction by 3, don't all of the coefficients get a factor of 3? So it's not just one H2S, there's actually 3 of them now. There's now 3 sulfurs. There's now 6 hydrogens. There's now 6 electrons. So I'm changing the coefficients of all of them. Same thing with the reduction reaction. Now it is 6 electrons, 8 H pluses, 2 nitrates, 2 NOs, and 4 waters. And now you add them up. It can get kind of complicated here. So notice how things cancel. We got the electrons cancel. What else cancels? Only some of the hydrogens cancel. I think we're left with 2 of them. And then I think that's it. So this got really messy. So we have 2 H pluses, 3 H2S's, 2 nitrates, 3 sulfurs, 2 NOs, and then 4 waters. And then that should be balanced. And now the new idea here is 6 electrons were involved with this redox reaction. That is what allowed us to add those 2 reactions up. I scaled everything up to 6 electrons so I could get them to cancel in the background. Because notice how you don't see any electrons in this redox reaction, but they are there. They got canceled in that background. All right, we'll do one more, and then I'll do the demo. Okay, another one. So, okay, yes. This question, very involved. There's lots of steps. On an exam, can we ask you to write out a full balanced redox reaction like this? No. So this is how we ask it in a clever way so we can make it a multiple choice question like this one. Consider this reaction, a redox between permanganate and oxalate. So I'm not asking you write the balanced redox reaction. I'm asking you what is the stoichiometry between permanganate and oxalate? I'm asking you what are the coefficients in front of oxalate and permanganate? So that means you have to get the balanced redox reaction to figure out what is that ratio. Okay, so that's just the way around it that we force you to balance it correctly. Because if you don't balance it correctly, will you get the right ratio? No, you won't. Okay, so let's do it. So it's the same 7 steps. Do the half reactions, balance them separately, add them up. So manganese and permanganate, +7. So we see that manganese is going from +7 to +2. So manganese is being what? Reduced. So you don't even have to do it, but that means carbon in oxalate to CO2 has to be being oxidized. But we can check it too. I think we did it before that carbon was +3 and carbon in CO2 was +4. So yes, it's being oxidized. But you can also do process of elimination. All right. So those are my 2 half reactions. So we got my ox, we got my red. So oxidation, C2O4, 2- goes to CO2. Then MnO4- goes to Mn, 2+. Okay, now it's time for balancing. Balance the carbons. So I need 2 in front of CO2. Are my oxygens balanced? Yes, they are. 4 on each side. Are my hydrogens balanced? Yes, because there are none. So next I just add electrons. I'm going to add 2 electrons on my product side to make both sides -2. And that is consistent with an oxidation reaction. Now we do the reduction reaction. Are my manganeses balanced? Yes. Are the oxygens? No. So I need 4 waters. But now I screwed up the H's. So I need to add 4 H pluses to the reactant side. Now this is the hard part, the charge. So don't skip this, don't be lazy. Like inventory all the charge on each side. So on my reactant side, what is the total charge that you see? +3, yes, because it's 4 H pluses and a minus permanganate. And then on over here, we get, oh, it's not 4, sorry. How many hydrogens should there be? 8. Why didn't y'all say that? Just yell it. Just yell it. You know I'm wrong. Okay, it's 8. So then what is the actual charge on the reactant side? +7. Yeah, I knew that was wrong. And then on my product side, it's +2. So I just need to make them match by adding the least number of electrons possible. So how many is that going to be? 5 electrons on which side? The reactant side. So +5 electrons. Boom, now it's balanced. That one was definitely more involved. Okay, so there is my redox reaction for my reduction. Okay, so how am I going to add these two up? The first reaction, I'm going to do what to it? Multiply by 5. And then the second one, I'm going to multiply by 2. So my new coefficients are going to be 5 oxalates, 10 CO2s, 10 oxygens. Those are my new coefficients. Then for the permanganate one, 10 electrons, 16 H pluses. No, that's not right. No, that is right. Yeah, that's right. 2 permanganates, 2 manganeses, and 8 waters. Now we add them up. So it doesn't look like really anything cancels except the electrons. So this is a 10 electron process. Okay, N is 10 in this case. And then we just add everything up. So this reaction is 6 H pluses, 5 oxalates, 2 permanganates, arrow, 10 CO2s, 2 manganese 2 pluses, and 8 waters. So let's answer the actual question. And that was, what is the ratio between permanganate and oxalate? I'm asking you, what is the stoichiometry between oxalate and permanganate? So the answer is a 2:5 ratio. And that's how we ask it on an exam. The answer would be 2:5 or 5:2, whatever. Right? But in order to get that, you have to balance the entire reaction. All right? But that's how we make it a multiple choice question. So we'll end right here with a demo where, look at this balanced reaction. So I actually just have it rewritten right here. It's the same one we just looked at. So the method we've been using all this time is the method of half reactions in acidic conditions, where we add H plus to balance the hydrogen. So there's a significance there, all right? So the demo I'm going to show you is highlighting the redox reaction here. Permanganate is a very bright purple compound. Manganese 2 plus is colorless. So I have that up here. So I'm going to show you the reduction of permanganate by a reducing agent. I'm not using oxalate. I'm using a different reducing agent, but it doesn't really matter. What matters here is that permanganate is a very, very highly purple compound. Here I just added a tiny bit of it. Make it brighter. Let's make it brighter. I didn't add enough. Okay. All right, super purple, right? That's super purple. That's MnO4 minus. Okay. This is, I'm going to add the reducing agent to it. All right, the reducing agent. So in this reaction, it's oxalate is the reducing agent. I'm going to add a different one, but it doesn't really matter. It's colorless. It's what's hopefully going to reduce permanganate down to manganese. All right, it's nitrite if you want to know, but it doesn't matter. Okay, so what do you think will happen when I mix a permanganate and a reducing agent? Do you think permanganate's going to get reduced to manganese 2 plus so it becomes colorless? Yeah, let's see. You'd think so. Okay, so see it's purple? Okay, so. Do you think a reaction happened? No, it didn't. Interesting, but that's weird. I added permanganate and a reducing agent and nothing happened. But look closer at this reaction. What else is required? Okay, water, there's a lot of water there. What else? Acid, H+, is also a component of this reaction. So here, I have a little dropper bottle of sulfuric acid, so let's see what happens. Boop. Okay, did a reaction happen? Yeah, so now finally by adding just a couple drops of H+, I was able to convert all of that permanganate to the manganese 2+, which is colorless, but it took acid to do that. So that's what it means to balance in acidic conditions. We need that acid there. Yeah.
So